So today we're going to be continuing waves, talking about waves. Now let's do a quick review. So there are two type of waves that we talked about 2 weeks ago. The first type of wave it's called a transverse wave, right? And so transverse waves, the particles, these dots vibrate perpendicular to the direction of wave motion. All right. So again, the particles themselves don't move with the wave, right? Because the wave only transfers energy, right? The waves don't transfer matter. That's a very important concept. Waves do not transfer matter, they only transfer energy. And so these are transverse waves. We call these transverse waves. Other type of wave is called longitudinal waves. Right, so longitudinal waves have particles that vibrate parallel to the direction of wave motion, right? And you can see this particle over here varying back and forth, back and forth, back and forth. And while the wave might be moving to the right, the particle doesn't move anywhere, right? Again, that's an important concept. And we talked about sound waves last week too, or rather 2 weeks ago, right? And so sound waves are longitudinal waves. Sound waves are longitudinal waves, and that's really just how sound travels. And you can see the compression and rarefaction here, right? So if I go back here, right, you can see the compression. The compression is where all these particles are the most compressed, the highest point, and the rarefaction is the part where it is least compressed, right? The point of least compression. And you can see that as we go along. Now, today we're going to be talking about, we're going to be concerned about, well, how fast do waves move? Right? How do we calculate the speed of a wave? Because waves, we know that waves move, right? They move in a certain direction, but how fast do they move in that direction? Okay. How fast do they move in that direction? Because, well, for example, sound waves do need to get from a speaker to your ear. It doesn't just happen instantaneously, right? It takes time, and I'm sure all of you know that there is a speed that sound waves do have a certain speed. It is not universal. It depends on what medium it is traveling through. What medium it is traveling through. All right. And so again, let's go let's do a bit of a review. So this wave right here, a wavelength, right? A wavelength is one wave cycle. Now that's the length of one wave. Now if I could, yeah, that's the length of one wave. And this is your equilibrium position, right? It's the middle where the wave deviates, and so the amplitude is from the equilibrium point to the highest or lowest point, and so that's going to be your amplitude. And amplitude measures energy only, right? And this is what was discussed in the last video. Amplitude only measures energy, or rather, it's closely related to energy. All right. Now, I'm going to ignore period for now. And I want you to focus on this side right here. And I want you to focus on a new word that I want to learn. And it's going to be called frequency. And maybe you've heard it in real life before, or maybe you have an inclination of what frequency means. Frequency is how many wave cycles or oscillations, and oscillation is the up and down motion, right? That's what oscillations mean. It's the up and down motion, or rather a cyclical motion. How many wave cycles or oscillations occur in a given amount of time? Right? You can see the clear difference between the top wave and the bottom wave. So there are more wave cycles, right? If we take the wave cycle to be one wavelength, right? One wavelength is one wave cycle. Then clearly the wave on the top wave has more wave cycles. And so there is a higher frequency. There is a higher frequency of oscillations on the top wave when compared to the bottom wave. And then the bottom wave has less oscillations, right? Less up and down motions. And so it has a lower frequency. It has a lower frequency. Well, if you compare and I neglected to actually input this, so I just realized that this would be a good comparison. Let's actually replicate. Let's put this here. Sure, why not? And so, and then that's what I drew there is one wavelength, right? That's one wavelength. So you're starting from the bottom, or rather equilibrium position, and going to the next equilibrium position. That's gonna be one wavelength, right? One down and one up, or rather one up and one down. So that's one wavelength. That's a wavelength of this wave. And you can see that if you have a higher frequency, then your wavelength is going to be shorter. And if you have a lower frequency, your wavelength is going to be much larger. And so we have this where we have this inverse relationship here now. There is this inverse relationship. Now let's go back to this part. And so the speed of a wave, the speed of a wave formula, it's on the bottom right, is the v is equal to frequency times wavelength. And so times lambda. That's just the symbol for wavelength, lambda. And now you can see what's going on, right? So the higher the frequency, the lower the wavelength. The lower the frequency, the higher the wavelength, the longer the wavelength rather. And so longer and shorter wavelength, my bad. So, and which is explained by this formula. If the speed of a wave is constant and if frequency goes up, then lambda must go down, and the vice versa is true as well. Now let's talk about period. Also, actually, I want to talk about frequency again. How many wave cycles or oscillations occur in a given amount of time? Usually that's in 1 second. We take that to be 1 second. And so the unit for frequency is hertz. Unit for frequency is hertz, and well, it should be a lowercase z, and it's or seconds -1, right? So that's a unit. That's a unit for frequency. So usually when we're talking about frequency, and usually on your problems, they want how many things occur in 1 second. All right. So if you're given the amount of time is 1 second, how many wave cycles or oscillations occur in 1 second? That's what you're gonna do. So the period time is so period on the other hand is how much time it takes uh for one complete up and down cycle of a wave, right? So we know that one complete up and down cycle is a wavelength. Well, how long it takes for that to go up and down is the period of this wave. So now I want to talk about electromagnetic waves. So this is a contrast to sound waves. Now we talked about sound waves, and all the waves that you've seen require particles to travel through, right? Sound waves, you wouldn't have sound in a vacuum, in a space, right? You wouldn't have sound in space because there aren't as many particles in space. Very It's very vast amount of space, and the particle density, the matter density, is very, 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 very low in space. So you wouldn't have sound in space, right? And if there weren't any particles for sound to travel through, right? If there weren't any particles vibrating, you wouldn't get sound. You wouldn't get a wave. And we call those type of waves mechanical waves. So waves that need something to travel through, we call them mechanical waves. There's another type of wave on the other hand, and if you're mostly familiar with it as light, light is a wave. And we call waves that do not require a medium to travel through as electromagnetic waves. They can travel through space. And there's a reason why I'm saying electromagnetic, and we'll have one lesson on why it's called electromagnetic, maybe, or rather, it's going to be uh, part of another lesson. But gamma rays, light, visible light, X rays, ultraviolet, microwaves, radio waves are all electromagnetic waves, which mean that these do not require any medium to travel through, right? So we know that light travels through space, and we know that there's not that light does not require a medium. So long wavelength, and so I want you to focus on this side right here. And so the lower your frequency, the longer your wavelength. Because even if we go to this formula right here, it's also on your reference table. Velocity is equal to frequency times lambda times wavelength. Which means that if my velocity stays the same, and if my frequency goes up, then my wavelength must go down, and vice versa. And the velocity of electromagnetic waves is always constant. The velocity of electromagnetic waves do not change. Or rather, it's a fallacy. It's erroneous to say that it's constant. It is constant in a vacuum, a complete vacuum. In a complete vacuum, the velocity of an electromagnetic wave is 3 times 10 to the 8 meters per second. But once you start shining light through a medium like water or air, the velocity slows down just a bit. Right, the velocity changes. So in a complete vacuum, the velocity of an electromagnetic wave, the velocity of light, the velocity of gamma rays, the velocity of radio waves is 3 times 10 to the 8 meters per second. And in addition to this formula right here, velocity is frequency times lambda. Sometimes you can use, oh, that's actually the wrong formula. Oh yeah, this is the wrong formula. V is equal to D divided by T. I'm sorry. Oh, almost didn't catch that. That would have been bad. So V is equal to D over T. That's the formula for velocity. And so you can use that as well. Now let's get to solving. Let's get to solving these problems. Number 1. A space probe produces a radio signal pulse. If the pulse reaches Earth 12.3 seconds later after it's emitted, what is the distance from the probe to the Earth? And we know that the velocity of a radio signal pulse, right, the velocity of radio wave is 3 times 10 to the 8 meters per second. D is equal to D over T. So V is 10 times 8. D is that, and then 12 is T is 12.3. And they're going to multiply, because we want to cancel out all these exponents. 12.3 times 3 times 10 to the 8. This is going to give you most likely 36.9 times 10 to the 9 meters. And we're going to simplify it, and that becomes, or rather, it's 10 to the 8 meters. I'm going to simplify now and becomes 10 to the 9. And that's the distance. Distance of radius of a crest. What's the speed of this wave? So 2 is exactly the same. 2 is the same thing as this. You're using this formula right here. Number 3. Number 3. So let's actually erase all of this. So it should be on your reference table, right? We know that the speed of a light wave is 3 times 10 to the 8 meters per second. And they wanted to figure out, well, how much time does it take for light to get from the sun to the earth? On your reference table, it should give you the distance from sun to earth, right? On your reference table, on the first page, you should be able to find a value for the distance from the sun to earth. If you can't, you can always Google it. But it should be on your reference table. I would use the number on your reference table. So that's that. We just went over 1 to 3, right? Because 1 to 3 just uses the same formula. So now let's talk about 4. It's about number 4. A diagram below represents a periodic wave traveling through a uniform medium. And if the frequency of the wave is 2 hertz, right? So that's that's how you measure a frequency, hertz, Hz. The speed of the wave is what? And so this problem, we're most likely going to be using this formula, right? Frequency times lambda. And lambda is your wavelength. So we want to figure out, well, what is our wavelength? Let's take a look at this drawing, right? So that's, I think that's pretty accurate. For the most part. For the most part. And so we know that one wavelength, and it's wrong to take the wavelength of this wave to be 6 meters, right? It's kind of tricky. Because we know that one wavelength, there has to be one up and then one down. Okay, so this is one wavelength, right? That's one wavelength. And if we know that this is how long one wave cycle is, well, we can figure out, well, from here to here is also one wave cycle, or the wavelength of this wave. Or alternatively, I can go from here to here, and that's one wavelength, right? This is also one wavelength. And so as long as you figure out, well, if the wavelength, as long as you figure out, well, there's one up cycle and one down cycle, then you know that's one wavelength. And you know that's a wavelength of your wave. Which means that this length is universal. I can put this over here. I can start over here and end over here, and that's still the wavelength of this wave. And now that you know this, it's saying that from here all the way to here is 6 meters. Okay, so let's actually erase this part for now because that might be a little bit confusing. Let's actually erase this part too. So it's saying from here to this middle part over here is 6 meters. But if we also know that the wavelength of a wave is this long, well then how long is this line? From estimation, I can already say that if this is 6 meters, this is probably 4, right? Because this is half of wavelength. This is just half a wavelength. This is half a wavelength, which means that this is going to be 2 meters, and this wavelength is going to be 4 meters. Okay? So the wavelength of this wave right now is 4 meters. The wavelength of this wave is 4 meters. So now we have everything we need. We want to figure out, well, what is our velocity? Our frequency is 2. Our wavelength is 4. And that must mean 2 times 4 is 8 meters per second. Yeah. C. C is the answer. 5. Same thing. You're gonna use for number 5 is pretty much just is that 6. Same thing. Yeah, 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 yeah. Same thing. Yeah. It's the same thing. Using the same formula for number 6. Good stuff.